should be equivalent through the Yau-Tian-Donaldson conjecture to the existence of certain canonical Kähler metrics in the first-term class of L. So K polystability should be equivalent to the existence of a constant scalar curvature Kähler metric in the associated Kähler class, so in the first-term class of L. So these are so-called canonical metrics. So the point is that this should give you some canonical representative of the Kähler class. So I won't really go into the history behind these ideas and what all of the results are, because this has been a very active topic for the last probably 40 years at least at this stage. But I will say that the results are strongest for Fano varieties, and I'll mention the results quite explicitly in that case. So the results and a lot of the recent activity has been particularly in the case of Fano varieties. But the story is much more general than that. So for me, what I'll mean is just that the line bundle L that you choose is equal to the anti-canonical class. So you're requiring that the first-term class of X is a Kähler class, where the anti-canonical class is ample. And in both cases, both from the point of view of moduli theory and from Kähler geometry, the results are essentially complete, at least for smooth or smoothable Fanos. So the first result is a theorem in one direction due to Tian and Biermann, and in the other direction due to Chen, Donaldson, Sun. So this is the link with the Kähler geometry. So the result essentially proves this conjecture relating K stability to the existence of canonical Kähler metrics. So the statement is that X minus Kx admits a Kähler Einstein metric. Now I'll get into the definition of all of these things later in the talk, but for the moment, this is essentially supposed to be motivation. So a Fano manifold admits a Kähler Einstein metric, which in particular is CSCK, if and only if X minus Kx satisfies this purely algebrogeometric condition of K stability. So Tian showed in the late 90s that if the Fano manifold had discrete automorphism group, then the existence of Kähler Einstein metric implied K stability. Biermann generalized that to arbitrary Fano manifolds, and then Chen, Donaldson, Sun proved the converse, which is in many ways more difficult, namely K polystability implies the existence of a Kähler Einstein metric. For moduli, the results are again complete in the smooth or smoothable case. So these are results due to Odaka, Li Wangzhu, Zhu Shuang. And actually, it's a very long story. Many people have contributed to it. It's, well, spotty Sun Odaka, Odaka spotty Sun in the case of Del Pezzo surfaces, for example. But the ultimate answer is that there exists a projective moduli space, projective separated moduli space of smoothable K polystable Fanos. So smoothable comes in essentially because these results used analytic techniques apart from the final one, namely the projectivity. So Fano varieties. So then these all have Kähler Einstein metrics. So from the point of view of analysis, you could consider this as a moduli space of Fano manifolds admitting Kähler Einstein metrics with a natural compactification, or from the algebrogeometric perspective, you just think of this as a moduli space of K polystable Fano varieties. So the existence of the moduli space is due to Odaka, Li Wangzhu. Projectivity is due to Zhu Shuang, following ideas of Cadoni Padak-Falvey, who considered the case of Fanos with discrete automorphism group. Just to mention beyond the Fano case, another case where this is kind of all well understood is the case of Calabi-Yau varieties or canonically polarized varieties. Then actually many algebraic geometers are very seriously interested in moduli spaces of canonically polarized varieties. This is these KSVA moduli spaces, and similarly for Calabi-Yau varieties. A result of Odaka actually says that Calabi-Yaus and canonically polarized varieties are automatically k-stable. So these also fit into this kind of general theory of forming moduli spaces of k-stable varieties. In general, there are many, many partial results. I'll only mention one because this will be kind of important later. So for general polarized varieties, there are many results, but in particular, the following one is the one that I want to emphasize, which is proving one direction of this Yau-Tian-Donaldson conjecture, namely existence of canonical metrics implies k-polystability. So again, a theorem that many people have contributed to. I'll just mention Donaldson, Stoppa, and kind of most recently, Biermann, Darvash-Liu. But it's a long story. So the result is that if XL polarized variety admits a CSDK metric, that implies that XL is k-polystable. Okay, so this is the kind of motivation, the sorts of results that we were motivated by in our study of fibrations. Before turning to fibrations, I'm going to actually give you the definition of k-stability. So I think this is maybe not something that's come up so explicitly in the previous talks, particularly because in the Fano case, there are various ways to reinterpret the notion of k-stability that do seem to be quite special just to Fano varieties. So I'll explain the definition of k-stability quite precisely. Okay, so we'll take now a normal polarized variety. I won't require smoothness anymore, just normality. We'll take X. And I'll change my notation a little bit. So I'll change it to H is the ample line bundle. So we have a normal polarized variety. So k-stability, essentially the definition contains two steps. First of all, you take some degenerations of your polarized variety. These are called test configurations. So these are degenerations induced by C-star actions. To each test configuration, you associate a numerical invariant, which is called the Donaldson-Fataki invariant. And k-stability then just gives you control over the sign of the Donaldson-Fataki invariant for all such test configurations. So I'll first of all define a test configuration. So a test configuration, so I'll write this as curly X. So this has its own line bundle, curly H, and a map down to C. There's a C-star action on C, and I'll ask the C-star action lifts to this variety X and lifts to this line bundle H. So a test configuration for XH is, so curly X is a normal variety. This morphism curly X to C, I'll require that this is flat. I'll require that H is a relatively ample, so ample over C, ample on the fibers. I'll just require a Q line bundle. Essentially, otherwise you could just scale everything, so the Q doesn't really make much of a difference. And the crucial point is that the fibers away from 0 in C are all isomorphic to the thing that you care about, namely XH. So with curly X, T, curly H sub T, so this is the notation for the fiber of the morphism pi over the point T in C. This is isomorphic to XH for all T in C star. And then the point is that the central fiber you have kind of no control over whatsoever. This could just be an arbitrary scheme with maybe lots of components, very bad singularities, but it's a degeneration of your original variety that you cared about, namely XH. Okay, and now I want to define the numerical invariant, which I'll define using the kind of intersection theoretic approach due to Odaka and Wang. So we'll set, first of all, mu of xh, this is just a topological constant independent of the test configuration. So I'll define this to be minus kx dot h to the m minus 1 over h to the m. So h is the dimension of x. These are just intersection numbers. You could think of them more from the differential geometry point of view as integrals of representatives of these cohomology classes if you wanted. But yeah, in algebraic geometry, this is just an intersection number. The next step is to compactify this family over C to a family over P1. So this is a trivial family away from T equals 0. So I can equivariantly compactify it to a family over P1 instead of C just by adding the trivial family at infinity. So we compactify to something I'll kind of abusively denote as xh over P1 still. So this is the trivial compactification at infinity in P1. So as usual here, I'm thinking of P1 as C union infinity, the Riemann sphere. And the definition of the Donaldson-Pataki invariant, which is really a reinterpretation of the original version due to, well, Tian and Donaldson. The generalization, this theorem is due to Odaka and Wang independently, is that the Donaldson-Pataki invariant has the following intersection theoretic definition. So it's m over m plus 1 mu of xh, this topological constant, times h to the m plus 1. So somehow the point of compactifying over P1 is that I can now do intersection theory on the total space curly x, which is now a compact projective variety, plus h to the m dot kx over P1. So this is the relative canonical class. This is kx minus pi star kp1, the relative canonical class. Okay, so these are our degenerations, test configurations. This is our numerical invariant, the Donaldson-Pataki invariant, which is just some intersection number. And then case stability gives us control over the sign of this intersection number. So then the ultimate definition is that xh is k polystable if for all test configurations curly x, curly h for xh, the Donaldson-Pataki invariant is first of all non-negative. And also we can characterize the equality case. So the equality case should only happen when the central fiber is isomorphic to xh itself. I'm not saying that you actually get a C star action on x itself. So, and equality, so the Donaldson-Pataki invariant is equal to 0 if and only if the central fiber x0, h0 is isomorphic to xh. Okay, and this is the definition of case stability that we're going to try and replicate now for fibrations. If there are any questions, please just let me know and I'll be happy to answer them. What I'll consider now are what could be called polarized fibrations. This is a fibration of projective varieties where the base has an ample line bundle and the total space has now a relatively ample line bundle. I'll denote this as follows. We let pi from xh to bl be a polarized fibration, by which I mean the following. This is really just a fibration from x to b in the usual sense of algebraic geometry, so that pi is first of all surjective. The dimensions are different, so dimension of x is strictly bigger than the dimension of b, and also the fibers are connected. I'll require that b and x are both projective. This is a fibration between projective varieties. I'll require that L is ample on B. And I'll require that H is relatively ample. So again, this just means that it's ample on the fibers. So the sort of case you should think of, I mean, if you have any flat family, that'll give you a fibration. Actually, I think isotrivial fibrations are particularly interesting in this theory. So the example I'll give is projective bundles, because this is somehow quite distinct from the sorts of fibrations that come in, for example, studying birational geometry, in that here the fibers have a very large dimensional automorphism group because they're homogeneous, they're projective space. So the example is if I take E over BL, a holomorphic vector bundle, or I guess really an algebraic vector bundle, I take X to be the projectivization of E, and H to be the induced O of one line bundle on P of E. So then what we have is a fibration where all the fibers are projective space. The line bundle restricts to the O of one line bundle on projective space for all fibers, but we get some non-trivial topological structure because we've taken a non-trivial holomorphic vector bundle. So, okay, there's a deep theory of the study of vector bundles in complex geometry and algebraic geometry, but it seems there's much less of a serious theory of fibrations, and that's what we were trying to develop. In some sense, fibrations through, for example, the minimal model program seem to be the key to understanding higher dimensional geometry, and so we want to study fibrations in their own right. So let's give you an idea of what's to come. The point of what I want to do today is to define a notion of stability for fibrations. So we define a notion of stability in this setup. So for pi from xh to bl. And I'll define a notion of what it means to be a canonical metric on such a fibration. So a canonical metric in C1 of H, and we call these optimal symplectic connections. So this is called an optimal symplectic connection, such that the point is that really this is all kind of motivated by the vector bundle theory. For vector bundles, there's a well understood notion of slope stability of a vector bundle, really introduced by Mumford, and a notion of what it means to be a canonical metric on a vector bundle. These are Hermes Einstein metrics. And what we're doing is generalizing from projective bundles to arbitrary fibrations. So first of all, such that if X is P of E, H is O of 1, stability in our sense, so stability of this fibration, this is equivalent to slope stability of the vector bundle. So this is a generalization of slope stability of vector bundles. So this is a notion going back to probably the, I don't know, maybe the 60s or 70s for bundles over Riemann surfaces, and then particularly heavily studied in the 1980s through, well, work of Donaldson, Lindbeck, Yao, and for example, on the algebrogeometric side through work of Simpson. So first of all, stability is equivalent to slope stability of E. And this condition, this optimal symplectic connection condition, is really just the Hermes Einstein condition in this case. So optimal symplectic connections these are just Hermes Einstein metrics in this case. Hermes Einstein metrics or Hermitian-Yang-Mills connections. Okay, so maybe, at least personally, I kind of grew up as more of a Kähler geometry, more of a complex geometry, and this was really our motivation to try and understand the Kähler geometry of fibrations. From algebraic geometry, I think the point of view should be more related to moduli theory. So let me say that when the base is a point, there is at least conjecturally moduli of K polystable varieties. So again, sorry, I should say that when B is a point, so the whole theory collapses. It's just really the theory of K stability in constant scalar curvature metrics. So a fibration of a point is itself a polarized variety, and so you're just studying the classical case. I quite like this actually. It's viewing case stability and slope stability of vector bundles in the same setup, and that's, I think, quite a cool thing. So yeah, sorry, I'll mention my results about Kähler geometry, and then mention the kind of algebro-geometric importance of what we're doing to moduli theory. So the theorem, again, so the whole setup and all of the results are joint work with Lars Seknon. So our result is that if a fibration, sorry, XH to BL, so it requires smoothness. So this is a smooth fibration. So I'll also assume that B is smooth because I want to do Kähler geometry essentially, which admits an optimal symplectic connection. Then it's semi-stable in the sense of vibrations that I'll define later. This is then the direct analog of Donaldson's results for constant scalar curvature metrics and case stability. So he proved that the existence of a constant scalar curvature metric implies case semi-stability of the polarized varieties back in around 2004. And the point is that we conjecture that the converse holds, namely stability should be, or polystability should be equivalent to the existence of optimal symplectic connections, which would then generalize the Hitchin-Kobayashi correspondence for vector bundles. I'll now...
In your theorem, are you assuming that the fiber are smooth too? The fiber of the fibration are smooth?
Absolutely, yeah. So for me, a smooth vibration means the fibers are smooth. Yeah,
okay.
So in complex geometry worlds, this would be a holomorphic submission, yeah. Okay. I mean, of course, I'd love to generalize it beyond that case. But singularities are hard in Kähler geometry. Yeah, so for the moment, this result is about smooth vibrations, so holomorphic submersions.
Thanks.
Thanks. Okay, so we conjecture, this is the sort of moduli purely algebro-geometric part of our theory, which is really just conjectural at the moment. So we conjecture that one can form moduli spaces of polystable fibrations over a fixed space. So again, this is motivated by the vector bundle theory. It's a classical result that one can form moduli spaces of slope polystable varieties over any polarized variety. So this should be seen as analogous. This is the kind of vibration version of the classical result for vector bundles. So much as one can form moduli of slope polystable bundles over a fixed space. And in that case, you can even compactify. The compactification in this case seems very subtle, but we, in addition, for example, conjecture that you can form a projective moduli space, so compact, when the fibers are Fano. So this is a Fano fibration. I'd like to say that I think this is a kind of important point. So we form, or we conjecture that one can form these moduli spaces. I think the traditional view of moduli theory of polarized varieties does actually lose something, because I mean, these classical moduli spaces often don't tell you very much about families of polarized varieties. So moduli spaces of varieties, they often say actually quite little about the study or the structure of families of varieties that are being parameterized by the moduli space. So they often say little about vibrations. And I'll be a little bit more explicit about what I mean. So for example, projective space PM is K polystable. For example, I think now one can prove this purely algebro-geometrically, but it follows from the fact that Fubini's Studi metric is Kähler Einstein. But the associated moduli space is just a point, essentially because projective space is rigid. So the associated moduli space is just a point. So it's really not telling you anything at all. But actually there is a whole theory of projective bundles that people study to rectify this. There are many, there are really very many non-trivial families for any given BL, pi from XH to BL, where XB, the fiber, is isomorphic to PM for all B and B. One can really just projectivize any vector bundle. So this is the sort of situation that we hope our theory should be able to help in. When the moduli theory tells you very little, it's because the fibers have large automorphism groups, essentially. In that sort of case, one should really be more interested in the study of moduli spaces of fibrations over a fixed space than the actual moduli space of varieties themselves. So our conjecture would essentially remedy this. Okay, so now I'll get into the definition of stability of fibrations. I should really emphasize, I think, that the theory seems to me to be much closer to the theory of vector bundles than the theory of varieties, and that's actually quite a good thing because the theory for varieties is very difficult, especially away from the Fano case, whereas the theory of vector bundles is much more well understood. So, I mean, in terms of difficulty of the theory, it seems to me that this interpolates between the difficulty of the two problems. It's definitely harder than the vector bundle theory, but it seems to me to be definitely easier than the case stability of varieties theory, which means I think that there should be lots of problems that are actually somewhat accessible in this theory. But okay, before getting into what those problems are, what we can say about them, I'll define the notion of stability for fibrations that we're using. So it's modeled on the definition of case stability, and that there will be a class of degenerations and then a numerical invariant that we associate to these degenerations. So I'll go through what the degenerations are first of all. These are what we call fibration degenerations. So we return to a polarized variety, or sorry, a polarized vibration, so XH to BL. So that polarized vibration. So kind of motivated by the moduli theory and really especially motivated by the analysis, we assume that the general fibers are K-polystable. So we assume the fibers XB, HB is K-polystable for B and B general. There are different variants of this hypothesis that you can make. This is the one that's actually crucial for the link with Kähler geometry. For example, one interesting case is when you have an isotrivial fibration where this is automatic. Of course, all the fibers are the same. So if the fiber is K-polystable, all fibers are K-polystable because all the fibers would be isomorphic. But this is a hypothesis that makes sense more generally. Okay, and now the push forwards are the direct image of the kth tensor power of H. So this is a coherent sheaf on B. And now the point is we've assumed that H is relatively ample over B. So by relative ampleness, we have an embedding of X sitting inside the projectivization of this coherent sheaf over B. So for example, if this was a flat fibration, then this coherent sheaf would be a vector bundle for K large. And this is sort of then like a relative version of the Kadara embedding. So we would have had X embedded in a projective bundle. In general, we just have X embedded in the projectivization of some coherent sheaf. We now take a degeneration of this coherent sheaf. So we let C star acting on curly E over B times C. So this is a coherent sheaf over B times C, which is flat over C, where the general fiber E sub t is isomorphic to pi star h to the k for all t not equal to 0. These are sort of like the vector bundle analogs of test configurations. And the key point is that actually these are very familiar objects in the study of vector bundles. In particular, if you take any subsheaf or subbundle of this vector bundle pi star h to the k, the so-called turning off an extension trick will produce one of these bundled generations. So if you take any f sitting inside h to the k, you'll get a degeneration of E to f direct sum, sorry, a degeneration from pi star h to the k to f direct sum pi star h to the k mod f through this turning off an extension thing. So these are something you can produce in abundance. Okay. So now the point is that X embedded in the projectivization of the general fiber, so we can define curly X to be the closure of the C star orbit of X sitting inside the projectivization of curly E. And we also get a line bundle by doing the same thing essentially. We just let the line bundle H be the restriction up to some scaling of OP of E. So this is curly E. One restricted to curly X. Okay, and the point is then that this has a morphism down to B times C. Just because the curly E, this sheaf had a morphism down to B times C, this endows curly X with a morphism down to B times C. So this then is, by our definition, this is what we call a fibrations generation. Okay, so this is our version of a test configuration for fibrations. Then one can produce genuine test configurations essentially just by pulling back this line bundle from B. So curly X and JL plus H, this is adjective notation for tensor power of line bundles, and this is the pullback from B. This is a test configuration for the total space, X with the line bundle JL plus H for all J very big. All you really need is some ampleness to get a test configuration from the setup. And the Donaldson-Patakian variant we show has an expansion in terms of powers of J. So this is equal to J to the N, what we denote W0 of curly XH plus J to the N minus 1, W1 of XH plus O of J to the N minus 2, where the W0 and the W1 will be the key numerical invariants of interest for our study of vibrations. And I should say here that N is the dimension of B. Okay. Now our notion of semi-stability is the following. So we say that pi from X H to BL, this is a semi-stable fibration. If for all fibrations generations, we have, first of all, W0 should always be non-negative. And this is essentially a consequence of the fact that the general fiber is K polystable. So W0 of XH is non-negative, and W1 of XH This is really the key condition. This should be non-negative precisely when W0 is 0. So this second condition is really the new thing that you don't see in the study of case stability of varieties. So it's a pair of conditions where the second one comes in precisely when the first numerical invariant is equal to 0. And as I mentioned before, we show essentially through work of Ross Thomas that this gives a new interpretation of slope stability of a vector bundle. So this really does recover the notion of slope stability, but that's really a theorem rather than something that's obvious from the definitions, and it's really a theorem due to Ross and Thomas. Just to give an example of what these numerical invariants look like, I'll mention the case of Fano fibrations, because I think this kind of quite strongly suggests that there should be a lot of geometry behind this notion of stability, particularly for Fano fibrations. So if H is equal to minus kx over b, the relative anti-canonical class, then this is what I'll call a Fano fibration. So pi from x minus kx over b to bl is a Fano fibration. And the numerical invariants simplify quite a lot in this case. Very explicitly, what you get is that W0 of xh. This is really just an expansion in terms of the intersection theoretic definition of the Donaldson-Pataki invariants. What you get is that this is equal to m over m plus 1. So I'll recall here that the dimension of x is equal to m plus n. The dimension of b is equal to n. So m is the fiber dimension. So this is L to the n dot h to the m plus 1. So L again is the pullback of L to curly x plus L to the n dot h to the m plus kx over now b times b1. Again, this is all computed on a natural compactification. So W0 you should think about as the Donaldson-Pataki invariant of the general fiber, the fibration. W1 is given as m over m plus 2, L to the n minus 1 dot h to the m plus 2 plus gamma of pi, and I'll come back to what gamma is in a moment, divided by m plus 1, L to the n dot h to the m plus 1 plus L to the n minus 1 dot h to the m plus 1, and then a relative canonical class term. And really the geometry that I want to emphasize is this constant gamma of pi. It's a very interesting number. So gamma of pi is equal to L to the n minus 1 dot minus kx over b to the m plus 1 divided by L to the n dot minus kx over b to the m. This is always non-positive, precisely because this is the constant that comes in when you're trying to study moduli of Fano varieties. The non-positivity here is a result of Cadoni and Paddock-Falvey. Oh, whoops. Essentially what's happening is that the moduli space of K polystable Fanos has a line bundle called the CM line bundle. This is the degree of the CM line bundle on the base B. And the CM line bundle, sorry, minus the degree. And because the CM line bundle is, well, ample, essentially, it's completely known now, this would be a non-positive number. Okay. So again, this really suggests to me that one should be able to study Fano fibrations, and there should be a lot of geometry behind the study of stability of Fano fibrations. So now I'll turn to the Kähler geometry. So this notion of an optimal symplectic connection that generalizes the notion of a Hermes Einstein metric on a vector bundle. Okay, so for those of you who know what a Hermes Einstein metric is, first of all, you need to fix a Kähler metric on the base B to make sense of the definition. So we'll do that again. So we fix omega B in C1 of L Kähler throughout. We'll take a relatively Kähler metric, omega X. So relative Kähler just means Kähler on the fibers. And what I'll impose, which is by analogy with requiring that the fibers are k-polystable, is that the fibers have constant scalar curvature metrics, and omega x is such an object. So omega b, which is the restriction of omega x to xb, so this should be a constant scalar curvature scalar metric for all b and b. Where I'll recall just that the constant scalar curvature condition, a Kähler metric induces a Riemannian metric, and this just requires that the usual scalar curvature in Riemannian geometry is constant. In Kähler geometry, you get all of these nice formulae, and these are that the scalar curvature S of omega is the contraction of the Ricci curvature on an n-dimensional manifold. This is the formula for the scalar curvature, where the Ricci curvature is produced by thinking of omega as a Hermitian metric on the tangent bundle. So omega to the n is a Hermitian metric on the anti-canonical class. And the Ricci curvature is the curvature of that metric. This lies in C1 of x, the first Chern class of x. Okay, so this is the kind of classical notion of a constant scalar curvature metric that is the same as the notion in Riemannian geometry. So for all of these canonical metrics, they're really curvature conditions. And in our case, the curvature condition will be to view omega x as a connection in the sense of differential topology, or really in the sense of symplectic topology. So omega x defines a splitting of the short exact sequence zero to v to tx to h to 0, where v is the vertical tangent bundle, so v is the kernel of d pi. So again, I'm assuming that everything is smooth here. This is a holomorphic submersion, so the tangent bundle splits, sorry, the tangent bundle fits into a short exact sequence involving the vertical tangent bundle and the horizontal tangent bundle. And the point is that you get a smooth splitting of this short exact sequence using this relatively Kähler metric omega x. So h sub x is the set of u in txx such that omega x of uv is equal to 0 for all v in vx. So really you're just requiring that v and h are orthogonal, but using the symplectic form. So the point is that this is really defining an Ehresmann connection, and in the symplectic geometry literature, they talk about omega x being a symplectic connection in this way. Going further, you get a splitting on all tensors. So induces a splitting on all tensors. And the following then is the curvature type operator. So omega x has a purely horizontal component, omega x sub h. And I'll define this mu star fh to be the horizontal component of omega x. So this is the definition. So omega xh, the purely horizontal component, I'll define to be mu star fh. The point is that you can think of this as the curvature of this Ehresmann connection. So this is the so-called symplectic curvature of the symplectic connection. And this is a reasonably familiar object in symplectic geometry. Okay, we need to do more. We're in Kähler geometry. We've got a lot more structure than this. So omega x, in addition, defines a metric on the relative anti-canonical class. So a Kähler metric induces a Hermitian metric on the anti-canonical class. A relative Kähler metric induces a Hermitian metric on the relative anti-canonical class. So it induces a metric on minus kx over b. So this is just the top exterior power of the vertical tangent bundle. And I'll define the curvature of this, or denote it to be rho. So rho you should think of as like a vertical, or sorry, a relative version of the Ricci curvature. We also get a vertical Laplacian, by which I mean a Laplacian operating fiberwise Laplace of V. Okay, now we're doing pretty well. We can set eta to be a function on X, which is the vertical Laplacian of the contraction of the curvature. So contractions of curvature come up when you're studying Hermes Einstein metrics, and this is very similar. The new thing is the presence of the vertical Laplacian and the fact that you also get a contribution from the curvature, the sort of relative version of the Ricci curvature. So there's a contraction of the horizontal component of this relative version of the Ricci curvature. The optimal symplectic connection condition isn't quite that this function is constant. That would be kind of bad for geometric and analytic reasons. Asking that eta is constant, for example, wouldn't give you a good PDE. And geometrically, what's happening is that the constant scalar curvature metrics aren't unique on the fibers when the fibers have automorphisms. Think of it like the case of projective bundles, for example, when any Fubini-Studi metric is actually a constant scalar curvature metric, and these are only unique up to the action of the automorphism group. So we kind of want to take into account the automorphism group of the fiber now. So we'll let E sub B be a this is really a vector subset, vector subspace of the space of real valued functions on the fibers. So these are functions phi sub B, who first of all integrate to 0. And the key point is that if you take phi B and you take the gradient with respect to the natural Riemannian metric on X sub B, and you take del bar of it, this should be 0. So this is saying phi sub B, the 1, 0 part of the gradient, is a smooth section of the holomorphic tangent bundle. And you're asking that this is actually a holomorphic section, i.e. del bar of it is 0. These functions are called holomorphic potentials. And these functions really do correspond to vector fields on the fibers. Holomorphic vector fields. Okay, then finally we let C infinity B, or sorry, E of X denote functions phi with phi restricted to XB inside EB for all B and B. So these are functions which generate holomorphic vector fields on each fiber. And we also net P from C infinity of X to C infinity E of X be an orthogonal projection. So this is a natural L2 orthogonal projection. So this is essentially involving this projection operator, saying that you only really care about the holomorphic vector fields on the fibers. And a technical condition comes in here that we assume that the fibers have the same dimensional automorphism group. So the dimension of the kernel, this operator del bar B, grad 1, 0 B, is independent of B. Of course, again, this is automatic for locally trivial fibrations, which are, I think, for this problem, a particularly interesting class to consider. This finally allows us to define an optimal symplectic connection. So omega x is an optimal symplectic connection if P of eta is equal to 0. But we'll recall that P of eta, this form eta, this is asking that the projection of this function which involved various curvature operators is 0. So you take your function, you only really care about holomorphic vector fields on the fibers, so you project onto an appropriate subspace of functions, you ask that that is 0. Okay, so the definition does not maybe look so natural. The first thing to point out is that this really is a generalization of the Hermes Einstein condition on projective bundles. So this generalizes Hermes Einstein metrics when X is equal to P of E. I won't really get into in so much detail why that's true, but essentially this rho is equal to mu star FH because a projected bundle is actually a Fano fibration in particular. Then this vertical Laplacian, actually the function that it's taking in its argument is an eigenfunction of the vertical Laplacian. So again, you kind of miraculously get to ignore that. And then again, by homogeneity, this projection operator doesn't do anything except project orthogonal to constants. So your condition becomes it really becomes the contraction of F is a constant multiple of the identity, where F is the curvature of the Hermitian metric, which is then the familiar Hermes Einstein condition. The second thing to note, which I think is maybe a clearer justification, which is a theorem rather than just maybe a short remark, is that optimal symplectic connections are unique when they exist. So if you have a fibration where the fibers have constant scalar curvature metrics and the fibers have large automorphism group, relatively CSCK metrics aren't unique whatsoever. This is an additional PDE that gives you uniqueness. So these are unique up to the action of the automorphism group of the fibration. When they exist. Okay, and I'll end with a formal statement of the main result, which relates this optimal symplectic condition to stability. So this is, again, a result with Lars Sekman. So this says that the infimum over omega x, relatively CSCK, by which I mean CSCK on each fiber, of the L1 norm of P of eta is bounded below by minus the infimum over the set of all fibration degenerations of JW0 of XH plus W1 of XH divided by something like the L infinity norm of for fibration degeneration. These are on the right-hand side, though they may not appear so, all completely purely algebra geometric quantities. And the point is that the left-hand side is independent of J, the right-hand side isn't. So you get the results that I actually stated earlier. So if a fibration admits an optimal symplectic connection, it is semi-stable. So this proves one direction of our kind of main conjecture that the existence of solutions to this PDE should be equivalent to an algebra geometric notion of stability for the fibration. I won't say anything about the proof beyond it mirrors some of the techniques of Donaldson's analogous result, this lower bounds on the Calabi functional paper. There are quite a lot of new techniques that we need to develop, which kind of force us to use these norms, which aren't quite as geometric as the ones that Donaldson is able to use, because the situation geometrically seems easier. So yeah, thanks for listening. That's it.
So thanks for the nice talk. Are there any questions?
I have a question. Is there, hi, let me, is there a moment map interpretation of this notion of connection?
Well, okay, that's absolutely a good question. I conjecture that there is, but we don't know what it is. I think the problem seems more tractable for locally trivial vibrations. I mean, the issue is somehow that I don't know what plays the space of almost complex structures on a fixed symplectic manifold. So, I mean, my conjecture is basically, yes, this should be a moment map condition, but we don't know what that moment map condition actually is. So yeah, it's I think an important question for future research.
Thanks.
Any other question?
Yeah, I have a question, if I may. In your conjecture about the moduli space, is that including singular fibers or
Yeah,
not?
so if you're taking the purely algebro-geometric approach, the singularities of the fibers don't really seem to come into the story whatsoever. Certainly, if you ever want a compact or projective moduli space, then you need to include fibrations with singular fibers. So basically, our conjecture is that purely algebro-geometrically, one should be able to form moduli spaces of polystable fibrations, including fibrations with singular fibers. And for example, for Fano fibrations, we even conjectured that you should get a compact moduli space. And for compactness, you see, even for vector bundles, you need to allow singularities if you're going to get a compact moduli space. So yeah, singularities
So
are...
you conjecture both compact and moduli for singular ones.
Yeah, look, I mean, it's easy to conjecture things. It's much harder to prove them.
Sure,
I mean, I'm not saying we can actually prove any of this, but yeah, certainly we conjecture that.
Cool.
But yeah, I mean, it seems very difficult.
This story never ends. We keep moving to new generalizations. Yeah, it's good. I like it. Thank you.
Thanks. Yeah, I apologize then for generating. Yeah.
No, it's good. It's good. I'm happy that it never ends. That's very good.
I have a question.
Mm-hmm.
Yeah. Hello.
Hello. Yep.
Yeah. I'm just wondering. I mean, what about a single negative fiber? I mean, what about say curve family? What do you say about a curve family? I mean, of a vibration of a curve. Vibration of a curve. Yeah.
Yeah. So you're asking, I guess, does the story simplify over Riemann surfaces, or?
The fiber are Riemann surface. Yeah.
Oh, I see. Okay. Well, so from the point of view, because we have this projection operator P, the only interesting case from the point of view of analysis is when the fibers have continuous automorphisms. So when the fibers are Riemann surfaces, the only interesting case is when the fibers are P1. Actually, I mean, already that story is very deep. This is slope stability of rank 2 vector bundles. But yeah.
So your formulation doesn't work for like a fiber is canonical polarized?
Well, in that case, essentially, you should think about like any fibration is automatically stable because the fibers are K stable. I mean, it's really the difference between the fibers being K polystable and K stable. When the fibers have discrete automorphism group, you don't get this interesting Pareto moduli theory. Like essentially, coarse moduli spaces are very good when you have things with discrete automorphism group. They're not so good when you have continuous automorphisms. So the story seems more interesting, for example, when the fibers are Fano, when they can have large automorphism group.
I see. I mean, you kind of do family moment map of the fiber, right? I see.
Yeah. So yeah, again, I'd love to have a moment map interpretation.
I see. Thank you.
Thanks.
I also have a small question. Do you know something about the structure of the automorphism group of the fibration when you have one of these special?
Yeah. So, I mean, this sort of problem is usually much easier on the kind of differential geometry side than the algebraic geometry side. And indeed, on the differential geometry side, we have a theorem that says, if a smooth fibration admits an optimal symplectic connection, then the automorphism group of the fibration is reductive. And even further, it's a complexification of the isometry group with the optimal symplectic connection. So, I mean, it's a nice thing, actually. What you see is precisely the automorphism group of the fibration coming into this story, which, I mean, again, suggests there should be quite a lot of geometry to what we've been doing. Yeah.
Thanks. Any other question? So, if not, we can thanks Rui again and the meeting today. Yeah.
Thanks for listening. Yeah.
Bye.
Bye.